we need to know the different ways in which you can get 3 aces and 2 kings. All right, so it's not always easy to visualize, especially since I didn't really give you a ton of space. But yeah, you could do a tree diagram. You could do a sample space. You could kind of do what I did last time. Oh, I don't know why I jumped like that. But we want to consider the different ways in which you can get those 5 cards, and then the probability of getting those particular 5 cards. So what I'm going to do is I'm going to start off with the event that it's an ace, an ace, an ace, a king, and a king in that specific order. All right. And then we find the probability of that happening. Then we just got to figure out the different ways in which we could have an ace, an ace, an ace, a king, and a king. Maybe it's a king, king, then ace, ace, ace. Maybe it's king, ace, ace. You know, there's all sorts of different possibilities. So we want to be able to figure that out too. All right. So we'll start off with this case. Probability of getting an ace times another ace times another ace times a king times a king. Oop, forgot the P. All right, so just those, or that one particular arrangement. So there's 4 aces in the deck out of 52 that are aces. Once we select one of them, there's 3 cards in the deck out of 51 that are aces. We've removed 1 ace. We've removed 1 card overall. After we've selected our first 2 cards, there's only 2 aces left in the deck out of 50 overall. But then when we switch over and talk about the kings, well, now we're back to all 4 kings being there. You actually have a better chance of getting a king now, because normally the probability of getting a king is 4 out of 52, but I just removed 3 cards from the deck. Right? If none of those were kings, then your chances of getting a king have now improved. All right? So 4 out of 49. And then getting another king would be, there's 3 left, there's 48 cards overall. All right, so we could run through the computations here. All right, the numbers are going to be a little funky. On the bottom, we could represent it as a permutation, just like we did above in the previous question. We're starting off with 52 cards, and we want a selection of 5 of them. All right, so we want a selection of 5 of them. I'm going to put the hat on the 5 there again. Now on the top, we could just crunch the numbers. But we could also look at it as a permutation. You know, so we have 4 available aces, and we're going 3 slots. So that would be a permute 4, 3, and then a permute 4, 2. But I mean, it's just as easy to multiply the numbers. So, you know, the reason we didn't do that up here is because the numbers got pretty big pretty quickly. But here you could say, okay, well, 4 times 3 is 12, times 2 is 24, times 4 is, 96? And then times 3, okay, so maybe it gets a little dicey after that, 270, 282, maybe? I don't know, we'll see. That's why we have calculators. I always try to do it in my head first. Goes back to the old idea of you're not always going to whip out the calculator. 288, said 282. Not always going to be able to or want to whip out a calculator. So it's kind of nice to at least try to use that muscle. And for me, it might actually be the only muscle I use on a daily basis. So what I want to do now is figure out the different ways I can make a selection from the 5 cards that have 3 aces. 3 aces, and specifically 2 kings after that. All right. So, and and again, I mentioned this before, you could consider the case of, well, I make a tree diagram and just go from there. But what I'm going to do is I'm going to figure out what 5C3 is. Oh, I forgot. We use different notation now. All right, I'm going to say 5 over 3 in those elongated brackets. All right. So what that's going to do is give me an arrangement, or I'm sorry, a combination, number of combinations of 5 things taken 3 at a time. All right. So that's basically saying you have 5 individuals and you want to break them up into groups of 3. Right? We can do that. And that'll tell us the number of different ways that the A's can be kind of dispersed throughout the distribution. All right. But again, and I'll do it just for the sake of the fact that this is the first time in a week that we're doing a problem like this. I'll at least take you a little bit of the way. If I were to say, all right, I'm going to get an ace, 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 king, king, but in any order, then it could be the case that I get an ace, ace, king, king, ace. You don't have to write this down if you don't want to. The ultimate thing is that we can come up with the number of different groupings that you could have rather than what those individual groupings are, because there will be no difference in the probability from this one to any other grouping that we can come up with. So you might have ace, king, king, ace, ace, king, king, ace, ace, ace. All right, so we're up to 4, but maybe the kings aren't adjacent to one another. All right, so I'm gonna pull this out for a sec. I'll bring it back in a little bit. I just want to have a little bit more room. So you could have maybe the first card was a king, but then you got an ace, then you got a king, then the rest were aces. All right, maybe it was a king and an ace and an ace and a king and an ace. All right. So I'm basically starting off with this, kind of looking at it like you have king, king, ace, ace, ace. Now let's see what happens if I just slide the king, the second king down the line a little bit. All right. So then it could be king, ace, 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 king. So kind of like a bookending deal. All right. So now we're up to 7 possibilities. But then you got to think about, all right, well, what if they didn't occupy the first position? So you started off with an ace, then you had a king, but the 2 kings weren't adjacent to one another. So maybe there's an ace, a king, and an ace. All right. Maybe it was ace, king, ace, ace, king. All right. Now, if you're kind of done with this, where you're like, all right, enough, then you're kind of where I want you to be, because you don't always want to have to show the entire distribution. You just want to know how many elements make up the distribution. All right, so these are all the different ways that we could have aces and kings. There's one more possibility, which I'm just kind of creating a little space for. I was hoping to have it like be in alignment a little bit. All right. Maybe you started off with a couple of aces, then a king, an ace, and a king. All right. If you did it, if you went one more where you had ace, 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 then the last 2 would have to be king, king. We already have that. So this is 10 possible arrangements. So instead of doing all that, we just look at the number of ways that the group of 5, or the 5 cards, could be broken up into groups of 3. All right? Because we talked about this last time, but it's not the most intuitive thing. Well, actually, let me amend that. It is intuitive if you think about combinations, if you think about counting and probabilities and things like that fairly frequently. All right? But for a newbie, it's not the most intuitive thing. All right? And that is, anytime you create a group of 3, you're indirectly creating a group of the leftovers. All right. So I have a group of three, which are my aces. I want to know the number of different ways that they can be spread out among 5 possible outcomes. Everything else is going to fill in the gaps, right? And everything else would be the case of the kings, right? So in the NumWorks toolbox, we use this bad boy here to get our 5-3, but we already know that that's going to be 10 because we just listed them all out. All right. And one of the reasons, aside from just showing you that you could do it this other way, the other reason I show you this particular technique is if you're ever in a jam and you want to figure out a probability, you don't need a formula. You just need to have an idea of the number of ways that the things can occur. All right. So it's this here multiplied by 10. So I need that 288. So 288 multiplied by 10 is going to be 2880. And on the bottom, I just need to permute 52 and 5. So it's in the same menu. And again, just to refresh your memories, toolbox is right here. All right, it's right next to the clear button. So you hit, well, in the calculate menu, hit the toolbox, you go to probability. Normally you start off up here, scroll down to see probability, you'll see combinatorics, and then you'll see the stuff that we need. Permute in this case, and we're putting in 52 and 5. So 3, 1, 1, 8, 7, 5, 2, 00. And I also mentioned this last time, but again, a week ago, that we want the fraction answer because that's the most exact form. But in order to truly understand what's happening, you may want to kick it over to decimal form. All right, so 2880 divided by that previous answer, that's going to give you something ridiculously small. All right, so I'm going to write that whole decimal out. 9.234463016 E negative 6. And of course, I did not give myself enough room to write that, so let me just slide some stuff over. Oh, not you. I want you coming. I want you to stay right there. All right. So this number, E negative 6. That E in the calculator, oops, that's not a highlighter. That E in the calculator is scientific notation. It means times 10 to the negative 6th power. All right, so that's what that reference is. Whenever you see an E, I don't know why the calculators use that. I guess because it's probably easier to just include that than times 10 to the, and put it in exponent form. All right, but what this means is that we would slide our decimal point over, this decimal point right here, over to the left 6 spots. All right, so you move it over 6 spots, that's going to create 5 zeros. So point 0, 0, 0, 0, 0, 9, 2, 3. All right. So what that's telling me is that to deal 5 cards to a person and expect that they're going to get 3 aces and 2 kings is remote to the point of being practically impossible. All right. Now, impossible would be 0, so it's not technically impossible, but it's very small probability. So I wouldn't expect that to happen. Now, that's the case where you deal 5 cards straight, one after the other. In a game of, for example, poker, that's not how it goes. You deal around, right? So let's say there's 5 people playing, and you deal the first card to each of the 5 people. Now, if I'm thinking to myself, I want to make sure I get an ace, or I want to make sure I get a king, the probability that 3 aces will be gone in that first round of dealing is so small to be practically impossible. All right, so it gives you a little bit of hope that there's going to be an ace waiting there for you if you need it. All right, so yeah, it's it's tricky stuff, but that's why we consider all the possible outcomes, right? And that's why games of chance are so challenging. Right? So we're going to kick over. Oh, actually, I wanted to talk to you a little bit more about the quizzes. So let me do that. I'm going to pause the recording here, or stop it. I'll merge it again tomorrow. And I'm going to say, for example, all right, we're going to find the number of different arrangements of the letters in the word I'm going to give two words. The first one, I'll say word. And the second one, I'll say, just want something with repeats in it. I mean, I guess I could go with a lot of different possibilities. Let's say happiness. Here's hoping I spelled that right. Pretty sure I did. 4th grade spelling bee champion of Dutchess County. No big deal. All right, so if I want to rearrange or create an arrangement of the letters in the word word, any of the 4 letters could occupy the first position of the new word. All right, so any of the letters in word, there's 4 letters, word, can occupy the first position. But then once one of those letters is placed, so let's say I place R as my first letter, then I only have 3 possibilities for the second letter, W, O, and D. Let's say I place W as the second letter. Then I only have 2 possibilities left, O and D, and it really doesn't matter. Let's say I placed a D, I'd have 1 possible letter as a result. All right, and that would be O. So that gives us 24 possible arrangements. Now, again, any of the first 4 letters could have occupied the first position. This is just one outcome. The R, W, D, and the O, that selection that I made, that's only one possible outcome of the 24 possibilities. Right? Because if I made a full-blown tree diagram here, I'd have W, O, R, D, branching off 3 ways, O, R, D, and so on. Maybe the D I'd branch off, O and R, and then the O would become an R or lead to an R. The R would lead to an O. It would continue on until you've listed all 24 possible outcomes. I'm not asking you what the words would be. I'm just asking you how many there would be. All right. So this would be a case of 4 factorial, which is 24. All right. So you look at that as kind of a recipe for handling these kind of problems. You say, oh, all I have to do is create a factorial consisting of the number of letters that make up the word. All right. So there's 1, 2, 3, 4 letters that make up the word. The issue that comes into play, I'm just going to slide this down a little bit. I'll complete that tree diagram later. I don't want to waste your time. Right? The issue that comes into play is something like happiness. Right? Well, really any word that's got repeated letters. Because right? What'll happen is, and let's say I did want to actually list out all the different arrangements for the letters in the word happiness, I could maybe swap the A with the H, do something like this. Oh boy. Just hitting buttons here. Okay. I could swap the A with the H and say AHPPINESS. Right, maybe I would switch the H with the P. Hey, you can see how this is going to take a while. or would take a while if we were actually going to do it this way. All right. Maybe I would switch the S with the S. Now that's where the issue comes into play. All right. Because if I take the letters in the word happiness and only switch the S's, I don't end up with a unique new word. All right. All I would be doing is taking an S and switching it with the S that's adjacent to it. Right? It's still the same word. So I'm actually counting a word that I don't want to count. Right? Swapping the A with the H, swapping an I with an N or an E with an S, that's all fine. But and it will happen, you get to a point where you swap two identical letters, nothing really changed. Right? Because it's kind of like, this is my first S and this is my second S. All I did was I made my second S into my first S and my first S into my second S. But the word itself didn't change. So it begs the question, okay, well, short of actually making a tree diagram for this whole thing, how do I do this? Well, we still start off with counting up the number of letters in the word. So I'm going to kind of put that aside and say happiness. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I would say 9 factorial to account for all the letters in the word. But then I would just look at the repeated letters. And again, well, not again because I didn't say this yet, but letters that repeat, they don't have to be adjacent to one another. You know, like Mississippi. Right? Those I's are all over the place. Right? They don't have to be next to each other. They are repeated though. All right. So what I do is I take the number of repeats, number of unique repeats. There's 2 of them here. Two of the P's and 2 of the S's. And I indicate a 2 factorial for each one of them. All right. The reason I'm doing that is because I not only need to figure out the number of ways I could arrange the letters in the word happiness overall, I also need to know the number of ways I can rearrange the repeated letters so I could divide that out so that I could remove any of that repetition. All right. So I'll show you a much simpler example. Let's say the word is wood, because we could figure this out. You know, there's only 24 possible arrangements of a 4-letter word. Some of them are going to be repeats. So how would we trim that out? All right. So, but before I do that, let me just get this answer here. 9. So in the factorial, so toolbox factorial, pop a 9 in there, and then divide it by 2 factorial times 2 factorial. 2 factorial is 2 times 2 is 4. So I'm dividing this by 4. So we're looking at 90,720. So if I had gone through the process of actually listing out all these possibilities, it would have been a good way to kill the semester. But in a much simpler case, if I take the word wood and make a tree diagram, put a little subscript for each of the O's. You look at, eventually you're going to see, okay, we're going to have some repeats here. But just kind of go through the motions, at least early on. If the first letter is W, then the second one has to be either O1, O2, or D. If the first letter is W and the second one is O1, then the third one would have to be O2 or D. If the first, second, and third letter is W, O1, O2, then the last one has to be D. W, O, D, so W, O1, D would lead to O2. All right, so far so good. We don't have any repeated words here. But when we get to the next level of this tree diagram, W02 would have to be followed by O1 or D. WO2O1 would have to be followed by a D. WO2D would have to be followed by O1. All right. So, and again, just to avoid having to do the entire tree diagram, I'll complete it all later. But if you look at the unique words that you get out of this, well, the first word, if I follow this pathway here, is going to be, I could strip away the subscripts, wood. The second one, so here, followed by here, then here, wodo. Oops. If I follow this pathway, I end up with wood. And if I follow this pathway, I end up with wodo. So I ended up getting double what I wanted, right, in terms of the outcomes. Because wood I already have, and wodo I already have. So these two are unnecessary. And when I continue the process, I'm going to find more and more unnecessary things. So again, instead of doing that, I would say there are 4 factorial for the letters in the word wood, and then I'd have to account for the repeats. The O occurs twice, so I do a 2 factorial to account for the different arrangements of the letter O and O. All right, so in each case, I had an O102 and an O201. Right, it's doubling up my possible outcomes. So I'd end up with a total of 12 unique possibilities here. But it's still, I guess, possible to use a tree diagram. It's just not always practical. All right. And then, like I said, I would continue on here and so on. So like I said, I'll do that later. I'll get the complete notes up for you. I don't want to make you do something and then tell you that I'm only showing you this because I don't want you to do it. Then it's like, well, why did we take 15 minutes to write this down in class? All right. So I just do the partial tree diagram to prove the point. And then later on, just so I have some good looking notes for you, I'll clean it up. All right. Same idea with the word up here. So that's one particular type of combinatorics question. It feels like a dumb type of question. Right? It's just kind of feels that way. It's like, when am I ever going to need to rearrange the letters in the word, whatever? And practically speaking, unless you like making anagrams, you're probably not. Right? But if you're thinking about different choices that you could make, one of the questions in the quizzes was, you get 9 colors of the car, 2 types of engine, and then I forget what the other one was. But this gives us different possible outcomes. Now, if it's like you have 2 different models of a car and they both have a 4-cylinder engine, it's like you're not adding anything to the conversation by counting that twice. Right? So it's more of a sorting and searching algorithm. Right? It helps you kind of limit the possibilities. If you think, it's alarming. If you think that you have 90,000 different possible outcomes, that's something that would turn you off to a particular situation. But if you know that you can limit that in some way, then it may be more manageable than you think. Right? So that's that. So probability distributions, I love this topic because it's almost like, now that we've completely mastered the area of probability, the mathematical area of probability, let's apply it. It's like, well, we spent like a week and a half on it. Like, did we really? Probability is such a deep topic, and it has applications in other areas, but it's not necessary to get into too much of that in order to really be a person who thinks probability-wise or probabilistically. Right? You can still think in terms of chances of something happening without going into chemical engineering. So it's just that. Now, what we're going to use probability distribution for is to determine something called an expected value, right? And I'll start off with a simple example. And in fact, I'm going to keep it simple because I want to finally, at long last, get us into some practical applications. All right. So, a probability distribution is the list of all possible outcomes in an event, in an experiment, and the associated probabilities. Right. So, I would say if I'm rolling a die, X would be the different types of outcomes. You could get a 1, 2, 3, 4, or 5, or 6 when rolling a die. The P of X column is the probability of each of those X values occurring. Right? So the probability of getting a 1 when you roll a die, 1 out of 6. Probability of getting a 2 when you roll a die, 1 out of 6. A 3, 1 out of 6. A 4, 1 out of 6. A 5, 1 out of 6. And a 6 would be 1 out of 6. Finding the mean of a probability distribution, I don't think we've really talked about this, but a mean is another word for average, which in a sense of probability means expected value. All right. Mean means average, familiar with the term average, but it also means expected value. We use the concept of a mean or an average in different ways. So like at the end of a course, when you find your average in a class, I don't think that's what you were expecting to get necessarily. Like maybe you wanted to get an A and you got like an 87, right? So that wouldn't be an A. I expected to get an A. Well, you didn't. And so what did you get? You got the average of what has happened in the past. That's fine. What we want to know in a projection sense is, can we get the average of something that will happen in the future, right? In a case like student grades, that would be akin to taking a class, getting a grade, going back in time, telling your former self, this is what I got the first time I took the class, right? Well, from that person's perspective, it would be the only time, right? So that's what I expect that you would get if you do what you do. Like whatever you're doing now, whatever approach you're going to take to being a student, if you do that and don't make any adjustments, this is what I expect to happen, right? So we're not time travelers, but we do have events that are predictable, right? Like rolling a die. You have a 1 in 6 chance of getting any of the outcomes. To find the mean, we multiply the X column by the P of X column. All right, so we're multiplying this column by this column. All right, so 1 times 1 out of 6 would be 1 out of 6. 2 times 1 out of 6 would be 2 out of 6. 3 out of 6, and so on. If we add up this column, that'll give us our expected value. All right. And just to add another layer here, that expected value has a symbol that we call, it's the Greek letter mu. It's kind of like a cross between a script U and a script M. I don't even know if it's really a script M, but still, it's kind of a funky U with an extra long tail on the right. So mu would be equal to, it's common denominator, it's all over 6. So 3, 6, 10, 15, 21. So 21 over 6, which if you put it in decimal form would be 3.5. Which based off of my definition, mean, average, expected value, the value that you would expect to get, I don't know that I would expect to get a 3.5 when I roll a die. All right. Now, if I rolled the die 100 times and averaged up my outcomes, now we're talking. All right. So, and like, it's not always the easiest thing in the world to do, but you can use a random generator. And I have to show you this because the next activity that we do, which is going to, well, I'll get into that later. But if you go into the statistics menu, so if you hit home and go into statistics, you have basically like a mini Excel spreadsheet, right? And you could put random numbers in here. All right, so if you go up to value V1 and hit enter, you'll see fill with a formula. And there's an option for random. Right? The notation's a little weird, but it's not terrible, because it's saying that it's going to give you a random number. It's kind of frustrating. One thing for students when they look at this notation, it's not exactly math notation. In fact, it's kind of closer to like some hybrid between Java and Python. And in fact, there's a Python editor in here, so they use some coding languages. The random with the closed parentheses after it, that's just Java speak. All right, so don't really worry about that. But the little explanation at the bottom is really what matters. All right, 10 random values between 0 and 1. So hit OK. I don't want 10, I want 100, for example, or 1,000. Well, you can only put 100 values at a time in the NumWorks calculator. So when it comes to getting really, really large data sets of random numbers, I know I talked about this like maybe 3 weeks ago, but for our next activity, you'll need to know that. So I'll go over it again. But I could type in a 100, and it'll create random numbers between 0 and 1 100 times, which is great. All right, the issue is I need random numbers between 1 and 6. All right, so that's one way that you can get random values right in there. Very easy to clear a column. Clear table. All in one shot. It'll ask you to confirm, because there's nothing I could tell you this. You may not have much experience with this, but with handheld calculators, there's actually not really much of a worse feeling ever than typing in 150 values and accidentally deleting it all when you didn't want to delete it. All right, so it gives you that extra message of are you sure you want to do this, which is really good. All right, so fill with a formula. I mean, you could go down the list and look for it, but these are really just templates. So if I go and hit OK on this, but then go into the squiggly brackets and clear that out or delete it, in the toolbox under probability, so let me make a note, toolbox, now my pen doesn't want to work, oh there it is, toolbox, it's really giving me a hard time, probability, random, hit OK. You see random with the parentheses, and then you see random A comma B. When you go into the fill with a formula, the template, those are just suggestions. You can modify those as much or as little as you want. All right. So I would select rand AB. All right. So rand int AB. Right, and actually, let me really get specific here with these steps, just so you have it, because you will need it. All right, so we go to home, statistics, V1, hit OK. That's all the stuff I got to get us into the fill with formula. All right, fill with a formula. then select the rand or random, that option, because it's already kind of pre-built for you, k less than or equal to 10. Then we go into the toolbox. Then we select probability, random, randint. You might prefer to just bring a die with you and roll it 100 times. Right, so select that, hit OK, and now I'm going to put in a 1, 6. All right, so this is in the NumWorks screen. This is what should appear. All right, but like I said, I want to do this 100 times rather than 10 times, because it is kind of like a question of being practical. Would I really use this function if I just wanted to roll a die 10 times? Probably not. All right. I would just roll a die 10 times and see what happened. All right, but then you hit OK, so I'm going to change this. This becomes 100. And now I have a list of random numbers from 1 to 6 happening 100 times. All right, so in a split second, all it took was these simple, like 300 convoluted steps. Fairly quickly, quicker, I can promise you this, quicker than it would take to actually roll a die 100 times to write the outcomes. This is saying that the first outcome I would get is a 6. When I roll the die a second time, it could be a 3, could be a 1, all right, it could be a 4. It's going to change depending on who's doing it and when you're doing it, because this is based off an algorithm, a random number generator, right? So, I got a 6, but you could have got a 2, right? Don't get alarmed if you try this and the person next to you tries it also and they come up with something different. Right? But then what I want to do is go to stats, which is in the upper right hand corner there. So you hit the up arrow, over, and hit OK. And if you go down the line here, you're going to see a mean. It told me that mu is equal to 3.64. All right. This is an experimental value. All right. This one over here is the theoretical expected value. All right. If I roll it, I talked about this when we talked about like the very first moments that we talked about probability. If I flip a coin 5 times, it is conceivable that all 5 times I get a heads. You say, "Whoa, it must mean that you get heads every time." Well, flip it 5 more times. Well, 1 out of the next 5 were heads, so now I'm up to 6 out of 10. You're like, okay, so it must be 60% of the time that I get heads. Then you flip it 300 more times, and 145 times you got heads. The other 155 times you got tails. Right? It's not quite where it should be. It should be 150. Right? That's what's happening here. Our expected value should be 3.5. It ended up being 3.64, but I only did 100 trials. All right. Still, you're not going to end up with an outcome of 3.64, 3.5 even. If you roll a die, no matter how many times you roll it, the outcome that you're going to get is going to be an integer value, like a number 1, 2, 3, 4, 5, or 6. But what this is saying is, if you roll it many, many times, on average, or the average of your total list of outcomes should be 3.5. Right? And because that's dead center of the distribution, it means that we're looking at a balanced distribution. Equal parts above that number, equal parts below that number. All right? So it goes along the lines of, if you think about the median, when you find the median of a data set, that's the middle number. You should have an equal number of values above the median as you have below the median. All right? So that's what this is telling us. We could find things like graphs, but doing it by hand is, I don't want to say it's obsolete, but it's not really necessary for us, because we could just go to graph on NumWorks. And you guessed it, look at the graph. All right, so we're going to learn about statistical graphs as we go, but for now, a histogram is probably the way to go. All right, and so it's giving me kind of a fluctuating distribution. It looks like I have fewer ones than I have everything else. But again, this is experimental. Oops. What we're going to do, and it's not going to happen tonight because I said I'd let you go early, but we're going to learn how to apply this. All right. So, and the reason why I showed you how to do it by hand is sometimes it's easier to find the mean of a probability distribution, also known as an expected value, by hand than it is to even type it into the calculator. So I wanted to show you a quick example. And next class we'll lead off with example 2 because that really feeds in nicely to our next project or activity. So New York State daily number, your goal is to select the same 3-digit number that the computer selects. You know, this first ball up is 2, and the second is 7, and the last is 4. All right. What we want to do is determine the expected value for playing the game. We have to make some assumptions because when it comes to games of chance, the better, I guess, I try to stay away from gambling terms, but the person that's playing the game controls how much is wagered in the game. Now, when it comes to lottery tickets, it's you pay $1, you get a ticket. Right? If you pay $100, you don't get like 100 times the value of the ticket. You just get 100 individual $1 tickets. All right? So it works a little bit differently than when you're playing a game like roulette. Right? So yeah, like if I want to put $100 down on black and I win, I'm going to get $100. If I bet $100 on a lottery ticket, well, I might just win the one ticket, but I'm not gonna get $1 back for each ticket that I purchased. All right. So the game works differently. What we want to do is figure out what this will mean in terms of our desire to play the game. All right. Noted. So your two possibilities are winning and losing. If you win, you're going to win something. They're saying here that if you pay $1 in your bet, you're going to get $500, right? Not really, right? Your net winnings would be 500 minus 1. That's an assumption that we have to make. When we talk about the I call it the trolley game, but it's really just modified version of roulette. You get your wager back. So if that happens, let's say I bet $1 and I win $500, I'm actually walking away with $501, but only 500 of that is new to me, which I'm happy about. Don't get me wrong. If I put up $1 and I walk away with 500, I'm feeling pretty good, right? But in this game, you purchase a ticket, cost you $1, you win. You've already spent $1, right? So you have a little deficit of $1. That's overcome by the $500, but you're walking away with $499. So that would be the net winnings. All right. So if I win, I'm going to win $499. If I lose my buck. There are variations of the lottery games where if I bet and win, they give me a free ticket. You know, it's like, hey, let's see if we could win your money back. Yeah, if that happens, that's fine. You know, like that's great. It changes the game slightly. You get the value of $1 back, so technically you win $500, but not all the games are like that. And it's to get a better sense of the probabilities, you're better off thinking of it as if you don't get your wager back, right? It kind of makes it a little bit hedgy. You know, it's sort of like, okay, let me figure out what the worst case scenario would be, and then go from there. All right, so X would be the number, or really the number of dollars I stand to win if I win, number of dollars I stand to lose if I lose. The probability of winning. This goes back to what I said before. We start talking about probability distributions, and I say, okay, now that we've mastered every aspect of probability, let's go ahead and learn how to apply it. And it's like, well, we didn't, but we can figure out this one pretty easily. Right? You're going to pay $1 to choose a 3-digit number. If that matches what the computer selects, then you win. All right, so the number of possible 3-digit numbers would go from 000 up to 999. That's 1,000 3-digit numbers. All right, 1,000 3-digit numbers. I don't know too many people that would select 000 or 999, but you know. And they're kind of wise to that. In the actual daily number, you can do a straight bet, which means that you choose the number, let's say 345. If the number comes up as 345, you know, first ball up is 3, and the second is 4, and the last is 5, then you win. But if 543 comes up, you don't win on straight play. But if you box it, they call it boxing your wager. It means that in any order, those numbers can come up. But the payout is $250 compared to the $500. All right. So it's actually still to your advantage to play with a box based off of the fact that you're allowed really 6 different arrangements of the same 3-digit number. So it's like I have a 6 in 1,000 chance of winning as opposed to a 1 in 1,000 chance of winning. I am 6 times more likely to win, but they're only paying out at half of the original value. So if I'm 6 times more likely to win and they chop off the winnings by 1/6, then I'd say, well, that makes sense. But if they only chop it in half, then I'm ahead of the game just by playing. Right? So I have a 1 in 1,000 chance of winning if it's straight play. That means that there's 999 times out of 1,000 that I'll lose. All right, and right there, that usually ends up being enough of a deterrent for people to wager. It's like, wait, 999 out of 1,000 times I'm going to lose this game? That sounds pretty awful. All right, but what I want is the expected value, so x times p of x. So 499 over 1,000. So just like we did before, I'm taking these two numbers and multiplying them. Then I'm going to take these two numbers and multiply them. So negative 999 over 1,000. All right. So that amounts to negative 500 over 1,000. Now, for our purposes, we're just going to be thinking positive is good, negative is bad. All right. But the more negative that the expected value is, the more bad it is. All right. So this ends up being negative 0.5. Now, there are units to this. All right. This is the same as $0.5. All right. So the interpretation of this is, in the long run, you stand to lose 50 cents on average. All right, so it's kind of a comparative measure. So the key is that it's on average. You're never going to lose 50 cents. I mean, if you're thinking, well, I'm either going to win 500 or lose $1, win 500 or lose $1. It's like, how would I ever end up getting 50 cents out of it? Okay. But what I'm saying is just like what we did with the calculator a little while ago, you have all these different possible outcomes. And you think, well, how would I ever end up with a decimal value? Well, if you take the number of outcomes, add them all up, and divide by the number, with the associated probabilities, then divide by the number of outcomes that you have, yeah, you could end up with a decimal. Just think of it this way. Let's say I play the lottery 5 times, and I'll just do it in the home screen. So I play it 5 times. I win the first time. I'm very lucky. Well, actually, I'm not as lucky. I still lost my dollar on the wager. All right. Then I lost the second time, and the third time, and the fourth time, and the fifth time. All right, so I played the lottery 5 times. So I got $495 as my net. All right, I'm still ahead of the game. I mean, that's what a lot of people will do. Is that like the daily number? I mean, you can win it. And what a lot of people will do is they'll say, okay, well, that buys me another 100 games before I have to worry about like being in the red, right? But if I take this number and divide by 5, I get a 99. Let me lose one more time. I just needed a decimal. I needed to prove that a decimal could actually work out of this. So if I play the game 6 times, I win the first time, beginner's luck, and then I lose the next 5 times, I'm averaging about $82 per game. All right. Now, it doesn't really feel like that. It feels like you won once and you lost the other 5 times. But if you play the game over and over and over and over again, all those different outcomes, they kind of blend together. And this is just one particular arrangement. I mean, you could look at it like, okay, I played the lottery 100 times and I lost every single time. But then on the 101st time, I actually won. Right? So that's divided by 101. So now my expected value would be about 3.95. So each game has, on average, been worth about $3.95. All right. This is really kind of like the poster child for if you win early, take your winnings and walk away. All right. Same thing with a casino. All right. If you don't, then you get into other things that are not always great. All right. Let's say you play the game 1,000 times and you lose every single time. And then on the 1,001 and first time, you win. Now I'm down $500, and I played the game 1,001 times. All right. So what this is saying is, on average, I stand to lose 50 cents every time I play the game. All right. It could be a lot. I mean, you could throw in, let's say, negative 20,000. All right, so I played the game 20,000 times, and I lost. Now, 1 in every 1,000 times I should win. So let's say I win 20 times. That's what I would expect to happen. All right, take that and divide it by 20,020. About negative 0.5. Right? So if you adhere to the probabilities and say, well, 1 out of every 1,000 times I should win, this is what I would win if I won. The other times I will lose, and this is what I'll lose if I lose, then around negative 0.5 should be your expected value in the long run. I can tell you, and we'll talk about this next time, in casino games of chance, your expected value is actually more favorable than even this simple game. So you think about it like, and people justify gambling. I mean, if you have a vice in life, you figure out a way to justify it. You know, so it's like, oh, well, I can do this as long as I don't do that. Like, I mean, you get into like drinking, drug use, gambling, anything that could be like a negative thing in your life, any other kind of addiction, you find a way to justify it, right? And so what somebody will say is, well, I'm not really gambling. I'm just playing the lottery. 365 days a year. $5 worth of tickets each day, right? As opposed to another person who is like up to 3 o'clock in the morning in Atlantic City in a casino, but that's the only time they've ever done it and the only time they're ever going to do it. That person looks like the degenerate gambler. It's like, oh, they just blew like $500. But that's a one and done. As opposed to the person who's in the habit, And it turns out that the lottery users usually spend more on average in lottery tickets than a person who casually goes to a casino will spend, right? Because, I mean, I don't know if you know anybody who's lost $15,000, $20,000 at a casino. I know I haven't. Right? Most people that I know, they go casually, they have fun, and then they, oh man, I guess it's not my night, and then they call it a night. All right. So there is no right answer, but the casino games have an expected value that's actually more favorable, and I'll prove that to you next time. All right. So 50 cents on average for every time you play a game, that doesn't sound terrible. But if I tell you that instead of 50 cents, negative 50 cents as the expected value, that I could promise you an expected value of about negative 3 cents. All right, so every time you play the game, on average, you stand to lose 3 cents. Not 50 cents, 3 cents, just pennies. Which game are you more likely to play? It's the one that's more to your advantage. Now, if you ever come up with a game or find a game where the expected value is positive, play that game over and over again until you can't play it anymore. All right, that's my one rule when it comes to this whole deep conversation regarding games of chance. Expected values are supposed to be negative in games of chance. It's supposed to favor the house. All right, and you look at it like 3 cents to an individual person on average. That's no big deal. The house is getting 3 cents per individual person that goes to their casino or any of their casinos at any point or all points throughout the day for however many times they play the game. Right? If you've ever seen the movie Office Space, that really gets the point across. Right? It's like the quick premise is they've robbed a company, but they didn't rob them for like $10 million all in one shot. They set up a program that would withdraw a fraction of a cent for every transaction. And before you know it, that added up to millions because that's something that the company wouldn't notice. Right? That's what a casino does to individuals. Yeah, a person's like, yeah, I won $10,000. But there's another 20,000 people that just lost $1. Slot machines. It's like, who's winning? The house is winning. Right? They can afford to shell out $50,000 in a jackpot because they know they're making that money back and then some in other ways. Right? That's why they comp you. Like, oh, you're going to play the casino. If you're too young, you don't know. But you go to a casino and you're playing, you're there for a couple hours, you rack up points, they bring you a couple of drinks for free, and then they give you a room for the night. It's just so that you'll consider staying a little longer. All right? So they'll get your money back, and then possibly they do that to enough people, they'll get more than their fair share. Let's put it that way. There's a reason why they always have those really high-end stores in the little mall areas outside of any casino, because the minute you win, they want you to spend it right back, right? Assuming that you're not staying in the casino and just giving it right back, right? So part of my discussion when it comes to probability is always a gambling responsibility component, right? Because it really is that important that you understand what they're trying to do, how the games are played, so that you don't get played, right?